and retired as Professor of Physics from Utkal University on 30th November 2008, holding many administrative posts like Dean, elected member of Utkal University Senate, Registrar, Control of Examinations, etc. during his long tenure. He had a brilliant academic record, first rank in physics honors from Mayurbhanj and recipient of Mayurbhanj Gold Medal as best graduate of Utkal University, first class third rank in the Utkal University in Masters of Science, first class third rank in Kolkata University in post MSc Associateship Diploma from Saha Institute of Nuclear Physics. He did his PhD in 1975 from Utkal University, postdoctoral in 1979 to 80 from Dortmund University, Germany. Another PDF from 1980 to 82 from Dublin Institute for Advanced Studies, Ireland. Associate from 1985 to 90 at Abdul Salam International Center for Theoretical Physics, Trieste, Italy. Visiting scientist in 1985 at CERN, Geneva, Dortmund University, Ulm University, Germany. He has 67 publications in very high impact journals, and he has got a lot of contributions in popularization of science. Just to name a few: Odisha Vigyan Academy Award 1999, book Anuru Antariksha, which actually inspired me to choose this topic before you, Atoms to Cosmos. Samanta Chandrasekhar Smriti Parishad, Noyagad Award 1990, Sarala Hi Sundara, book in Odia on 12 physics equations which changed the world. Simple is beautiful. Translated 2 volumes, Inventions That Changed the World of National Book Trust, New Delhi, India. Numerous articles, talks in school and colleges and TV programs. Translated autobiography of famous mathematician G.H. Hardy, a mathematician's apology. What is Life by Nobel laureate Erwin Schrödinger, and First 3 Minutes by Nobel laureate Stephen Weinberg into Odia as Jane Atmachintana, Jibana Kona, এবং প্রথম 3 minute respectively. Vigyana Pathe Pathe, a collection of essays on science, also he has written. Peer recognition, invited talks, chairing sessions in conferences on high energy physics. Biographical profile in 25th silver anniversary of Marquis Who's Who in the World 2007-2009. Member UGC 11th Plan Expert Committee. Member UGC Major and Minor Research Projects Evaluation Committee. Award Foremost Educators of the World 2008 Award. Best Citizens of India Award of International Publishing House, New Delhi, and 2000 Outstanding Intellectuals of 21st Century Award of International Biographical Center, Cambridge, England. A referee of Pramana, a journal of physics, Indian Academy of Science, Bangalore. Member Selection Committee of NIT Rourkela, OPSC, Odisha, etc. Besides this, Sir is a brilliant speaker and a very good human being. I know him for the last many years, and it's really, he was so kind in agreeing to my proposal of delivering a SOAFAL lecture sometimes, and anyway it materialized today. So with these words, I will request our Vice Chancellor, Professor Ashok Mahapatra, to kindly speak briefly on the objectives of SOAFAL and the way we have started the journey many sometimes back in 2021 on February 20th. Welcome you, sir.
Jai Jagannath. Good afternoon. I send my greetings on the occasion of Bahuda Jatra. Bahuda Jatra is a very auspicious day and in Hindu calendar, and we all respect this festival and pray Lord Jagannath that all of our citizens of the country should remain safe and healthy in this pandemic. I must thank Professor Lambodar Prasad Singh for his august presence as a lecture, giving a lecture. Just had his illustrious career in Utkal University. It only say that the place doesn't matter. If you can work, the sky is the limit. It doesn't matter where you or what you do. So it's for Utkal Gopabandhu Das, Karme Jiye Nara Karma Dinatara Ekamatra Manadanda. So what you do, that is more important. Where to do, what do we eat, what do we wear, how much, which has evaluated more than 499 medical colleges. Our institution had been numbered as 16. This only day for yesterday, that is on 7th of this month, the Carrier 60 has ranked our IMS some hospital 16 ranking. So I think we have made some impact for the states, for the country, and world as a whole. Coming to our students, we have so many specialties, 10 institutions: medical science, engineering science, dental science, pharmaceutical science, biotechnology, and hotel management, law, agriculture, veterinary science. And all these have added to our social cause. Our students are doing very well. They are socially concerned. They are involved in NSS. They are involved in NCC. They have adopted villages. They go and work for Swachh Bharat. They also work for Atmanirbhar Bharat. They also start startups. We have skill labs, research labs, and this last 21 year, even during pandemic, we have produced more than 2,000 Scopus Index journals, and highest impact journal was 91. That was in medical science journal published from Boston. And this way, the university has made a progress in last 16 years. It's a very young university. It started 2006, 2008, 18 we got a dim status, and we have got graded 2 autonomy. So we take students from NEET and JE. So we take very quality students. We have also more than 300 international students. Because of pandemic last 2 years, new students have not come. So currently we stand as an international student, 190 or so. We want to make it 10% of our total strength of student, 14,000. Our teacher-student ratio is 1:9. We have 47 girl student. If you look at the gender bias, you look at the inclusiveness, we give large number of students, between 30,000 to 50,000 scholarship per year. So we have to have education inclusive, student-oriented, and also qualitative and innovative, skill-oriented student education, in which we have made a dent. I hope that our students do well in the future. They learn from our esteemed lecturers, because carefully our lectures are lecture topics, and our lectures are well selected with a very large mass pool of eminent teachers, orators, philosophers, and also spiritual leaders, those who can innovate, those who can stimulate, and they could encourage our students. I hope our faculty and students and whoever hear these lectures must be benefited from the vast experience our eminent and highly respected teachers, those who are delivered these lectures. I think I stop here. Thank you very much. Jai Jagannath. God bless all of us. Thank you very much.
Thank you, sir. Thank you very much for your kind words. Now it is my proud privilege of welcoming today's speaker, Professor Dr. Lambodar Prasad Singh, to kindly speak on today's topic, Atoms to Cosmos. Sir. Sir, you can speak now. Please unmute yourself and you can speak, sir. ସାର୍ ଆପଣଙ୍କୁ ଅନମ୍ୟୁଟ୍ କରନ୍ତୁ ଆଉ କୁହନ୍ତୁ ସାର୍। सर आपण अनम्यूट करंतु सर शुभुनी just wait please.
Hello, can you hear me?
Yes sir, now you are audible.
Okay, thank you. Can you see the slides, please?
Yes sir, yes.
Okay, thank you. So I'm very delighted to be a part of this lecture program, and I must thank our famous Vice Chancellor of SOA, Professor Mahapatra, and Dr. Nachiketa Babu for giving me this kind invitation. Hello. To be a
Yes
part
sir,
of
you are audible sir.
Okay. To be a part of this lecture program. In fact, I am really indebted to the authorities of SOA for giving me this opportunity. And I hope I will be able to satisfy the high standard already set by the eminent speakers in these lecture series. So, without much ado, I must start my presentation. And what I'm really going to talk about is a topic which is really very expansive in nature. But since I was told that there will be students of various disciplines, so I thought this would probably not be completely out of place to talk about a physics subject, because I happen to be a student of physics. And what I've chosen is a topic based on my book, Anuru Antariksha, From Atoms to Cosmos. So, with these few words of introduction, let me start. Well, we are all students of science or technology, I suppose, and we therefore should have first inquiry in our mind as to what do we really mean by science. As we all know, science is in fact a quest to understand the mysteries of nature. And it is these mysteries of nature which have actually always attracted the human minds from time immemorial. And this has actually in course of time given us the entire edifice, what we now call science. So one of the leading mathematical physicists of 19th and 20th century, Henry Poincaré, in his very famous book, Value of Science, defines the attitude or the mindset of a scientist in these following lines. A scientist studies nature not because it is useful, but she or he delights in it. She or he delights in it because nature is beautiful. If nature were not beautiful, it would not have been worth studying. If nature would not have been worth studying, life would not have been worth living. So you see how passionately actually some people, some minds are in love with the mysteries of nature, with the laws of nature, and always are faced with the questions like, how does it happen? Why did it happen like this? What is the basic law that is governing these? Or these are erratic things which are happening all around us. So these are the kind of questions which actually drives a scientist, a true scientist, to study the nature in all its manifestations. So in fact, to start with, this endeavor was called philosophy, because we wanted to basically know what is happening, for what kind of reason, and what is the basis of such happenings. So it was called philosophy. That's why the highest degree in science, humanities everywhere, you see, is a doctorate in philosophy. It's never a doctorate in Odia or English or physics or mathematics. It's a doctorate in philosophy, because at the highest level, in fact, it is philosophy. Because philosophy in Sanskrit or in Odia means darsana. So that is the way we actually see the mysteries of nature. We see the working of the nature. We see beyond the manifest realities of nature. Because what we see, in fact, is not the real nature that is working, or the laws of nature that is working behind these phenomena. So let me proceed ahead. As I said, I happen to be a student of physics, and Rutherford, for example, once commented that all science is physics or else it is stamp collection. So, in fact, he was a physicist, so it's sort of natural to say this. But no, we know today that, in fact, science has sort of become extremely big in its collection of ideas, in its endeavor to work on, because it has migrated to areas which involves life. It has migrated to areas when it involves the entire cosmos. It has also migrated to areas which also involves very, very large things like stars and planets. It has also migrated to areas which are very, very small, like atoms, molecules, and even smaller ones. So what I have sort of catalogued here is that today, as physics stands, we actually investigate physical systems starting from 10 to the minus 16 centimeters, as small as that, to 10 to the power 28 centimeters, which is basically the size of the observable universe today, because we don't know what is the real size of the universe. But with our highest powerful telescopes, we have been able to see as much as 10 to the power plus 28 centimeters. So therefore, and that's what we call is the observable universe. So that is the length range which is being investigated by scientists at various levels. So, and similarly, we are also, what are we really looking at? We are looking at the laws operating under the veil of the phenomena, because we see infinite numbers of phenomena happening around us, but there are very few laws which actually governs them. Just for example, apple falling from the branches of a tree or the planets revolving around the sun, they are actually governed by the same law. So therefore, they are not different when it comes to understanding the laws of physics. So similarly, we have also gone from the very, very big, as I just said, from the study of the cosmos, study of the planets and stars, study of various bigger things like the earth and the interior of the earth, etc., to the study of the atoms, the interior of the atoms, like nuclei. We have also gone to the interior of nuclei to study the neutrons and protons. We have also gone deeper even to study what constitute actually neutrons and protons. And how do we study them? We study them, in fact, by sort of using mathematics. We call them the study that we were performing to study the larger objects till the beginning of 20th century, in fact, was called classical physics. Because most of the objects that we were studying, the physical systems, were large in their sizes. So therefore, whatever mathematics we used, we actually called them classical physics. Now we group them as classical physics. But once we started collecting experimental evidences of things which are not really amenable to classical physics, we wondered what is really happening. Why are we not able to understand them as we were able to understand things in the pre-20th century? Then the question arose, and then finally the answers also came, and we saw that we actually need a new kind of physics, a new kind of intuition to understand them. And that new phenomena was actually called quantum physics. So basically, as things stand now, we have a classical physics which we are describing. Most of the major macro objects that we happen to see around us. And when we go to the macro things, from macro to micro, then we see that the classical physics understanding doesn't really help us. We need a newer understanding, and that newer understanding, that new effort, the new attempt is actually called the new phase that actually entered in the beginning of 20th century is actually called quantum physics. And then while doing this, actually we came up many startling things, like what we earlier considered as different, we saw that they are not really different. Just like electricity, magnetism are considered different. But now we know that electric current can give rise to magnetic effect, magnets can also give rise to electric currents, so they are not different. Similarly, as time progressed, we could also see that energy is not different from the mass. Mass is basically a condensed energy, and energy is basically diluted mass or evaporated mass. So there is a interconversion between energy and mass. through the famous equation of Einstein, which many of you might have heard about, if not read about. That's E is equal to mc square. So energy is the same as mass. So energy is not visible to our naked eyes, but mass is visible to our naked eye. Irrespective of that, they are actually deeply connected to each other. The mass is same as condensed energy, and the energy is basically evaporated mass or diluted mass. Similarly, Einstein, through the genius eyes of Einstein, he was also able to tell us that the space and the time are also connected to each other. They belong to one entity that is called space-time. These are very sort of startling intuitions which actually appeared in the realm of physics in the early 20th century. Einstein's work was actually performed in 1905. The 1905, if you know, is a miraculous year of Einstein's life. He published 3 papers, and these 3 papers, in fact, brought in a huge revolution in the thought processes of physicists and science as a whole. So in that year, which is called Annus Mirabili, then miracle year of Einstein's work, he published actually one paper on the photoelectric effect, for which he got Nobel Prize, and that was in fact the first paper which said that the wave and particle are also similar. You cannot really distinguish them, waves and the particles. Waves usually are very continuous things. They don't have regular shapes and sizes, but particles have regular shapes and sizes. So people used to think that they are very different from each other, but Einstein said that wave and particle in fact can be unified. So therefore there was a unification of wave and particle. For example, light. We all knew that actually light propagates in the form of a wave. But when light interacts with particles inside an atom, inside a matter, it actually interacts like a particle. So as if it consists of particles. So therefore, that is in fact, that is the principle he used to explain the various experimental results on the photoelectric effect. You might have read in +2 or at some stage. So therefore, there was a unification of wave and particle. There was a unification of energy and mass. Earlier, there was a unification of electric field, magnetic field. So therefore, as we go along, actually we see that there is a unity behind diversity. Indians, for example, we always say that our culture is based on unity in diversity. So it is not just a social phenomena, it's just not a political phenomena, it's not just a cultural phenomena, it's in fact a natural phenomena. In nature also we see that whatever we consider as different, in fact as we learn more and more, as we learn better and better, we see that they are not really different, they share a common ancestry. Similarly, we are also, as I go along, I will probably tell you that a few minutes later, that some of these interactions which we consider as fundamental interactions, we are also trying to see if they actually originate from one uniform source, which is known as, in our parlance, it is known as unity of all 4 fundamental interactions. As I go along, I will explain to you. So therefore, this is where we stand. We are now basically studying physical systems, starting from very, very small, like 10 to the minus 16 centimeters, as I said, to the very, very large, like 10 to the power plus 28 centimeters. In fact, from the quarks, leptons, and nucleons, like neutrons and protons, to the entire universe as a whole. So we can take each of them as a physical system and study the laws which are operating there. So, and in course of these studies, we have also seen, as I said, many different things are in fact not different, but they have a connectivity between them, as if they are one and the same thing. So, it's in fact echoes what was already said in our Gita. Sarva bhutesu janekam bhavam abhyam ekshate avivaktam vivaktesu tadgyana vidhi satvika. So you see, Gita perhaps was written, let's say, 1000 BC, before Christ, or 1500 BC, or maybe a little later, I don't know. I mean, people give different dates. So even there, it was also seen by the seers, those who wrote those slokas, they also saw that in fact there is an underlying unity among the diversity. So all that we see in the entire world, there is a underlying unity. In fact, that unity was also proclaimed in our Upanishads by words like Tat Tvam Asi or So Aham. So therefore, when you look and ask the teacher, and look around and ask the teacher, who am I? Who is God? In fact, the teacher answers that you are the God.
Good.
Hello? So therefore, in fact, as you see that there is a unity between the smallest of the small part of the creation with the highest of the high part of the creation, the God. Because God we perceive as the one who creates the creation. But every little part of this creation, every minute part of the creation is in fact mirroring God in itself. So that is what in fact we physicists are gradually gravitating to. Thank you. So I go to the next slide just to tell you that how do we get actually information about the small things or the large things. For example, about the small things, we use, our eyes cannot see smaller things. We cannot see the virus. We cannot see the bacteria. We cannot see the air. We cannot see the molecules. We cannot see, therefore, the atoms. So there, what we use as our
So where I can see bacteria?
Sorry? Just a minute, please. I will answer questions in at
Yes, the questions will be answered at the end. So please
Okay.
keep quiet. Sir, please continue.
So therefore, we use certain instruments to perform the duties of a very powerful eye. So we use, in fact, microscopes to see smaller and smaller and smaller things. So you all know that every doctor, for example, is busy with his microscope.
Can I get a
Busy with his microscope, seeing the bacteria or the virus or something else. Similarly, you also see that there are people. So in that line, in fact, the highest powerful microscope that we have built is an electron microscope. Whether it is scanning microscope or it's a tunneling microscope, whatever it is, these are all electron microscopes, and they see very, very small things. In fact, I will tell you, I will show you the picture. You can see here a picture of atoms, in fact, seen by the highest or the most powerful electron microscope. If you use electron microscope, that is actually much more powerful than our visible ray microscope or light microscope. So, because the resolving power of electron microscope is much higher. Okay. Similarly, we also use telescopes. We have been using various kinds of telescopes since they were first used by Galileo in 1610. Galileo was the first person. He must have heard the name of Galileo. So he was the first person who used the telescope actually to see the craters in the moon, the satellites of the Jupiter, etc. So from then on, we have been making more and more powerful telescopes to see the objects which are very, very away from us. And even though they are very big, they also look very small because the distance between them and us is very large, extremely large. So I have given you here a picture of a space-based telescope. So you can see that the telescope is actually placed in the space around, let's say, 500 kilometers above the surface of the Earth in the atmosphere. It's revolving around the Earth and taking pictures of the universe, basically. So, and in different regions of the visible spectrum, like, as you all know, that light, in fact, has a spectrum of its own, which we call electromagnetic spectrum. We actually, our eyes are only sensitive to the visible part of it, from blue to the red, isn't it? And beyond red, we have higher wavelength light, like infrared, microwave, etc. Similarly, beyond blue, we have beyond violet, we have ultraviolet, we have X-rays, we have cosmic rays, etc., which are higher frequency or higher energy radiations. So that is why, in fact, the doctors always test see whether our bone is broken or not by using X-rays, because X-rays can pass through our flesh, but it cannot pass through our bones. So they basically see the image of the bones. So we have entire electromagnetic spectrum. We also have another wave which is known as sound wave. That's a longitudinal wave. That's a different kind of wave, but that is also used to study various things. In the military, we all use ultrasonic radars, etc., which can actually see where the enemy aeroplanes are, etc. So therefore, we also use sound wave to look around and see the various phenomena which are happening in nature. In addition to these two waves, light wave and sound wave, of late, only from 2017, we are also trying to see things with the use of gravitational wave. That has been detected already. It's a very, very feeble wave, very low energy. We cannot create it. But when, for example, two black holes collide with each other, or a neutron star collides with another neutron star, it also creates a wave. And those waves are called gravitational waves. And our instruments have been able to actually detect those. In fact, that was first detected, if I remember correctly, in 2007, and they have already got Nobel Prizes for it. So therefore, now we are using the three waves, gravitational wave, sound wave, and electromagnetic wave, to actually visualize various happenings in our universe. So you can call them as the three eyes of Lord Mahadev. Just like Mahadev has three eyes, isn't it? So that is how we progress. And I will give you pictures of the universe that we have seen through the space-based telescopes. You can see there was one picture of the universe, which was Kobe, 1992. Then there was another picture of the universe in 2003, the second one, the middle one. Then there is another picture, the last one, lowest one, which was taken in 2013. So you can see between these three pictures that gradually we are seeing more and more structure of the universe, and gradually we are also getting more and more convinced that the universe around us, in fact, is very uniform. You can see that. The first picture is not so uniform. There are difference of colors, and the colors are starker. The difference between the colors are starker. But that is becoming milder in the second picture, and that is almost very, very mild in the third picture. So you can see the discrepancies in the structures available, which are constituting the larger scale structure of the universe, is more or less getting uniformized. So in fact, the universe around us is more or less a uniform universe. So in fact, that's a basic principle with which we study our universe. Universe is homogeneous and isotropic. Homogeneous means every point in the universe is more or less like any other point in the universe. Isotropic means you look at any direction, they will always more or less look the same, more or less. Because in smaller distances, of course, you see many differences. You see a building, you see a tree, you see a lake maybe, so they are different. But if you look at the universe as a whole, whose size is of the order of 10 to the power plus 28 centimeters as its radius, then you see that it's almost uniform. So it's a question of taking average of the thing. So that way, universe is actually homogeneous and isotropic. Now here I have given you some pictures of the galaxies. There are many, as you all know, that we live in a solar system. Sun is in the middle, more or less, static, and then around it we have 8 planets, and that is our solar system. We are happy inside it. In fact, we are happy, very much happy living on the surface of a very small planet, which is our Earth, Mother Earth. And then we all know that we are getting almost the entire energy for our sustenance from the sun. A very small typical star in the galaxy that we live in called the Milky Way. Milky Way has billions and billions of stars. And sun is a very typically small star having its place in one corner of the galaxy Milky Way. And so you can see that our universe is in fact built with similarly billions and billions of galaxies. So every galaxy has billions and billions of stars, and universe has billions and billions of galaxies. So therefore, it looks like as if there are something like Avogadro number of stars in the entire universe that we have been able to see so far. So you can see some of the sizes and pictures of the galaxies. Some of them are completely spiral, some of them are irregular, some of them they have different shapes, some of them are spherical, some of them are elliptical. So they actually come in different shapes and sizes. But please understand that every bright spot inside a galaxy, in fact, is a collection of hundreds and thousands of stars. So, okay. So these are the pictures that have been taken using the very powerful telescopes. So the microscopes and the telescopes are basically playing the role of our powerful eyes, because we cannot see everything with our eye. Eye is only sensitive to visible rays. In fact, here I have given you two pictures of two black holes which have been seen recently. The first black hole that was seen is this one. So, is this one, which is actually the black hole that was flashed in all the newspapers of the world, and that was seen on 10th of April 2019. And the last black hole, the black hole which is sitting in the middle of our own galaxy, was actually given us on the 12th of May 2022, just 2 months before. So this is the first one, is the picture of the black hole which is sitting in the middle of our galaxy, just as the nucleus sits in the middle of atoms, just as seeds stay in the middle of the seed fruits. Similarly, the galaxies also have a nucleus of their own, and these black holes are actually forming the nucleus of the galaxies. So the distribution of a very big object in the middle and smaller ones around it is a typical architecture that nature is using everywhere. Just like in our body, we have bones in the middle, and then we have flesh surrounding it, and then we have skin to cover it up so that we don't have infections. Similarly, in the case of galaxies, we have black holes in the middle forming its nucleus. They are called, that is why they are called active galactic nuclei, because they are active objects. So they sit there, and then around it, billions and billions of stars are moving, though very, 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 very slowly. Just like sun is also moving around this galaxy of our own. This is the galaxy of our own, Sagittarius A. So these pictures are already possible. We are now seeing the black holes. Okay, so this is the wonder of wonders. This is what science is doing for us. So then I come to what is actually, so these are the benefits we are getting by trying to look at what this entire universe that we live in is constituted of, what do they really contain, how do these things work. So many things, there are questions, myriad and myriad of questions, and we are all trying to answer them in our own way, depending on our intellectual capability and intelligence. So, but anyway, the science or technology, these are all collective heritage of our humankind. As civilization progresses, these things also become better and better. They also gather more wisdom while going further and further. So now let me talk a little bit about the character of science. As you know, science is different from humanities. Why is it different? First is, it's an experimental endeavor. Whatever you say has to be experimentally verified, checked, whether that really happens or not. Just like in our villages, we used to hear from the village folks that jaha na dekhibo nijo noyane porote na jibo guru bachane. So therefore, you have to see it with your own eyes. Your own eyes means either you have to do it, so you perform experiments. When you see something, basically you are performing an experiment. So the whole thing actually started with Galileo. So he was the first person who developed a telescope. Then he looked at the moon, he looked at the planets, and then he was convinced that what Copernicus was saying, in fact, is correct. We have actually a sun-centric system, solar system. Sun is in the middle. Earlier, people used to think that Ptolemy, for example, was thinking that Earth is at the center and everything else is moving around us. But that's not true. We have actually a heliocentric solar system. So Then after Galileo, we had Newton, who explained many experimental results. Then I have just written three names because they are the three most important figures in development of physics. So Galileo, then Newton, and then Einstein. Newton developed basically what we call classical physics. He gave us also the rule of how light behaves. He gave us the three Newton's laws, how the material particle would behave under the action of a force, first law, second law, third law. He also defined what a mass is. Mass is basically the resistance to motion. That's what we call inertia. So mass is basically a measure of the inertia of a body. More massive object is, it has greater resistance to motion. So therefore it has more mass, or it has a greater inertia. So similarly, in course of our discourse on science, we also came to know, apart from experiment is an integral part of science. That distinguishes it from humanities. The second feature that distinguishes science from humanities is the use of mathematics. We really don't know why nature is so mathematical at its interior. But still, we all know very well that if we don't do mathematics, we will not be able to understand nature. That is why Galileo, in fact, in his famous book, first declared that the book of nature is written in the language of mathematics. If you don't understand mathematics, you will never be able to understand nature or natural phenomena or the physical laws governing the natural phenomena. So that's what. So these two things, experiment and mathematics, they actually distinguish science from humanities. And in fact, because of these two characteristics, science is universal. You can test it anywhere. You can test it in Bhubaneswar, in Tokyo. You can test it on the surface of Mars because of these two things. Because you can perform experiment, you can also calculate mathematics. Mathematical laws are also immutable. You can't say that 2 plus 2 can be 4 somewhere and 5 somewhere else or at some other time. You can't say that. So therefore, because of these two rigid restrictions, science is very different from humanities in its character. Then I've just written the quotations from about the mathematical character of science. So Feynman, one of the most prolific and creative scientists of last century, has said that to those who do not know mathematics, it is difficult to get across a real feeling as to beauty. The deepest beauty of nature, if you want the deepest beauty of nature, if you want to learn about nature, to appreciate nature, it is necessary to understand the language she speaks in. And the language nature speaks in is mathematics. Similarly, yes, and because of that character of science, what happens is usually all the highly creative scientists have done their best work when they're young. It looks as if mathematics and physics or science in general is actually a matter of, is a cultivation of young minds. As you grow older, your ideas get set and then you create nothing new. Nature, actually, you can't understand with old ideas. You have to create something. And for that creative mind, it is the young age which actually suits best. And that's what Chandrasekhar has written in one of his essays on beauty, truth and beauty. He writes, it is often the case that most important discovery of a scientist is his first. In contrast, the deepest creation of an artist is equally often his last. Because the artist or a literature actually matures with age, with experience. But a scientist or a mathematician doesn't mature. There is no room for maturity. Either you see the truth in a flash when you are young, or you more or less lose it for your entire life. That's what has happened. In fact, if you look at the age of the people who have created something new and have got Nobel Prizes in science, they have created those things when they were really young, between 20s and 30s, not beyond. Okay, so let us move. So, as I said earlier, that we have been, in course of our this quest to understand the laws of nature, we have also seen that there is in fact a unity in diversity. Our belief, and we also believe that whatever mathematics we are creating to understand the physical phenomena on the surface of the earth or around Earth will also work in the entire cosmos. That's also another extension, another big assumption that we are making, and it seems to work. That's the whole point. So our belief is that the laws of nature that works around us also works deep down at the micro level and up above at the macro level. So whether the physical system is very, very small or very, very big, they seem to be described by the same kind of mathematics. So therefore, that's a very relieving factor. Otherwise, we would have been at a loss completely. Just like suppose we would have elements numbering 9,560 or 10,000 or 100,000, then we would not have been able to do chemistry at all. It's just because we have only 92 natural elements, we have been able to study them. And this simplification actually, if you look around, this is a very magical thing that happens around us. The things are really simple, and these simple things actually build complicated ones. So therefore, we are able to study the complicated ones. For example, in a language, we have only 26 letters or 49 letters. Otherwise, supposing the letter number would have been, let's say, 5,000 or 100,000, then that language will be useless. We will not be able to master that language. So it is this simplicity underlying every phenomena that actually enables human mind to actually move ahead, to do research, to express things, to write books, etc., etc. So that's what I also quoted earlier. Sarva bhutesu janekam bhavam abhyamikhyate abhivaktam vivaktesu tasjnana viddhi sattvikam. That was also foreseen such a long, long time ago. So that's very nice. So now here I have given you a picture which is basically a model of the creation of the universe. So what is that picture? That picture is that our universe actually was created through a big bang, a huge explosion, Mahavisporana. So, and from that time onwards, and that time the universe was extremely hot, very hot. So therefore there was only energy or very small fundamental particles. They were all distinct from each other. There was no entity, as so to say. So, but as the universe expanded, our model is that from that time onwards, the universe is becoming, the space is becoming bigger and bigger and bigger. And because expansion causes cooling, so it is also becoming cooler and cooler and cooler. And as it cools down gradually, actually these small objects which were there at the time of creation, they are binding themselves together. And because of these bindings, first we saw that, for example, the quarks actually bound themselves together to form neutrons, protons. Then neutron protons means basically the nucleus was built within first 3 minutes of the creation of the universe. We use the first nucleus, hydrogen nucleus, tritium nucleus, helium nucleus. These small nuclei were actually built. And once the nuclei were built, they are positively charged objects, and electrons were also roaming around in a very high speed. But once the universe became cooler, the speed of the electrons also became lower, and these nuclei, which were positively charged objects, they attracted the negatively charged electrons and then started forming atoms. Once the atoms were formed, they are electrically neutral. They started forming molecules, either covalent bond or electrovalent bond, whatever it is, but they started bonding together. So that is a bound state. Single bond, double bond, all of you might have read in chemistry. So then molecules started forming. And then the universe was continuously cooling, and these cooled molecules started attracting each other because of gravitation. So you see, as the universe actually goes on its history of evolution, we see that first it was elementary particles, then it was the regime of nuclei, then it was the regime of atoms, then regime of molecules, and then once the molecules were started, gradually, through millions and millions of years, they started attracting each other through gravitation, and gradually the stars were formed, planets were formed, galaxies were formed, and that is how we actually have obtained the present structure of the universe. So that's a picture which is fitting very well with experimental observation, whatever has been made till today. So this is a picture of that. So here the universe actually gets created and then it expands, and as it expands it gets cooled, and because of this cooling actually particles started binding to each other. Once they started binding to each other, they actually the present structure of the universe gradually emerged. It's like people getting married, then forming a family, then forming children, then the family becoming bigger and bigger. So you have the entire society. That's how you get society. From society you get the entire country, etc., and from the entire world population, etc. So that is how we are actually picturing now the evolution of the universe. So now we say that the present universe where we live in, because why I am saying this, it could well be that there are many other universes. We never know. But we are only talking about our universe. Just like we were some 1920 or 30 before that, we even did not know that there are other galaxies. So we were happy in our own solar system. But 1930 Hubble, Edwin Hubble, first described that experimentally he found that we are not ours is not the only galaxy, there are also other galaxies. And those galaxies are also moving away from us, because he looked at the radiation which is coming to galaxies, and he saw that there is a rate shift in the spectral lines. And as you will study in +2, for example, science, that anything that is moving away from us and is emanating some radiation, then that radiation has to get rate shifted. The spectral lines must get rate shifted because of the motion of the source from which the light is coming. Just like we stand in a station, and if the train is approaching with a whistle, then the whistle actually has a higher pitch that is heard by us. Similarly, if the train is receding, then we know that the whistle has a lower pitch. So those are called Doppler effect. And that was actually observed with respect to the radiation which is coming from other galaxies also. So Hubble, in fact, first told us that we live in one galaxy, but there are also other galaxies, and those galaxies are moving away from us. Okay, so things are actually, that is how. So you see, it's only a matter of 100 years, from 1929 or 1930 to 2022, and the knowledge has developed to a vast extent. Okay, so that's what I have written here. So in course of the evolution of the universe, it was first particle physics, then nuclear physics, then atomic physics, then condensed matter physics, astrophysics, cosmology, and while it was, then we know that physics is being used in various other areas like geophysics, biophysics, psychophysics, econophysics, etc. And the entire physics actually is studied through our study. We have distilled only 4 kinds of interactions. Only 4 fundamental kinds of interactions. There are many, many interactions. For example, I am talking to you. Here you are able to hear me, but this is not a fundamental interaction. This is basically a residual of electromagnetic interaction. So all the phenomena that we have observed so far, studied so far in the entire universe, associated with our solar system or outside, have been logged into 4 fundamental interactions. One is called electromagnetic interaction. That is the interaction which is responsible for binding the atom to a stable state, electron and the nucleus, as I said some minutes before. Similarly, we have also gravitational interaction, which is basically responsible for the stability of our solar system. That is also responsible for stability of the galaxy. That is also responsible for stability of clusters of galaxies, superclusters of galaxies. So it is gravitational interaction which is playing the most dominant role in the macro scale, in the astrophysical scale, in the cosmic scale. It is the electromagnetic interaction which is playing a role here. For example, you are sitting under a fan. This is electromagnetic interaction. Similarly, we have also a strong interaction which is responsible for making the nucleus a stable state. A nucleus happens to be a stable object. If nucleus will not be stable, atom will not be stable. If atom is not stable, molecules will not be formed. If molecules are not formed, we will not be there. So see, this is a very beautiful sort of division of labor between the fundamental interactions. So at first, it was strong interaction, then electromagnetic interaction, and then gravitational interaction. There is a division of labor. And these three interactions are basically able to sustain our entire universe and all of us. There is another interaction which is a weak interaction, but that is only responsible for decay of the particles. Like beta decay, you must have read in +2, that there are some nuclei which are radioactive. Radioactive means they give rise to alpha ray, beta ray, gamma ray, etc. So beta ray is actually nothing but electron. So therefore, that was discovered in 1896, but that was actually understood completely in 1956. So it took something like 60 years to understand a particular interaction theoretically. So that is also another fundamental interaction. So we have 4 fundamental interactions like strong, electromagnetic, weak, and gravitational in order of their strengths. Gravitational visible objects that we see around us, lakes, mountains, birds, animals, trees, etc. Somewhere actually these molecules started becoming conscious. They actually